All right. So I've showed you some videos. We know that when a charge moves through a magnetic field, it experiences a force. The direction we get from our right-hand motor rule. The question is, how can we calculate the magnitude of the force? We're near the end of the semester, although I'd love to do a lovely proof. I'm just going to jump into it and give you the punchline. FB, the magnetic force on a moving charge, is equal to lowercase q, lowercase v, capital B. Except the V has a vector sign above it, the B has a vector sign above it, and underneath the V, we're going to put a perpendicular, and underneath the B as a subscript, we're going to put a perpendicular. Mallory, they have to be at right angles to each other, the velocity in the magnetic field, for my right-hand rule to work. Okay. What if they don't move perpendicularly? What if they cut across the magnetic field at an angle? Did I say angle? Okay. So technically, the proper equation, the magnetic force a moving charge feels, is QVB sine theta, where theta is the angle between the velocity and the magnetic field. I've showed that to you, but I'm going to tell you right now, we're always going to have them at right angles. By the way, what is the sine of 90 degrees? It's 1, which is why if they're at right angles, it's just QVB. Okay? So I wrote here, a particle carrying charge big Q or little q is moving through a magnetic field of strength B, making an angle theta. Since the component of the magnetic field in a direction perpendicular to the direction of motion is B sine theta, if you drew the right angle triangle, you would find that. Then it's QVB sine theta. So that's where that equation is from. Oh, what if they're moving parallel to the magnetic field? If they're moving parallel, what's angle theta between them? It's meant to be really obvious. 0. What's the sign of 0 on your calculator? No. What's the sign of 0 on your calculator? 0, no force. So if the charge is moving parallel, I kind of imagine that it's sneaking between the magnetic field lines and not feeling them. That's not really what's happening, but that's kind of what I imagine. For a charge to feel a force, it has to cut across magnetic field lines. If it doesn't do that, it will not experience a force. And for us, I'll have them cutting across at right angles. Okay? So I wrote on the next page, charged particles that move in a direction perpendicular. Well, since sine theta is of 90 is 1, you get QVB. So the maximum force is experienced when the particles move in a direction that is at right angles or perpendicular to the magnetic field, and that's what we're going to look at. So example 1, a proton moving at 1.7 times 10 to the 6 meters per second enters a 0.15 Tesla magnetic field at right angles, so we are at 90 degrees. What's the net force on the proton? Okay. What does it want me to find, Quinn? Nope, that's part right here, first question. I should have made it A and B. Say it again. The what force? The net force. The what force? The net force. Do I need to do a free body diagram? No. I am going to go straight to F equals ma, except no. What is magnetic force? It's not ma. What's our equation for magnetic force? Q, V, B, the one we just wrote. And can you find where that is on your formula sheet so we know what area we're at? I think I gave it to you. Did I give it to you lowercase q or uppercase q? I can't remember. Okay, whatever. So, lowercase q. It's a proton. (1.6 times 10 to the negative 19), that elementary charge. V, 1.7 times 10 to the 6th. B, that's the magnetic field strength in Teslas, 0.15. How many newtons of force will this proton experience? 1.6 scientific notation, negative 19 times 1.7, scientific notation, 6 times 0.15. I get 4.08 times 10 to the negative 14 newtons of force. Double check me. Same thing? Which on the proton scale is a massive force. Small on our scale, but what is the second thing they want me to find in this question? I'll call it part B, Braden. What does the last sentence ask me to find? Acceleration. Well, F equals what? Get the A by itself. It's going to be the force divided by the mass. What's the force? 4.08 times 10 to the negative 14 divided by the mass. It's a proton. It's going to be a really big acceleration. Do you get 2.44 times 10 to the 13th? Wait a minute, Mr. Dewick. I thought the speed of light was 3 times 10 to the 8th. This is bigger than the speed of light. Doesn't that violate relativity? Is this a speed? What is it? It's an acceleration. That acceleration, if it was accelerating for like a second, then yes, it won't accelerate for very long. The time frame that this would accelerate for is so small that you wouldn't reach the speed of light. But while you were accelerating, believe me, you'd be cooking. Also, this acceleration isn't changing its speed, it's changing its direction. What was it, Mr. Dewick? Times 10 to the 13th? Okay. Before we turn the page, as far as I'm concerned, Mallory, in this equation right here, QVB, there's 4 variables, F, Q, V, and B. If I give you any 3, you can find the 4th. As usual. Let's look at a pretty cool application. Let's consider an electron as follows. Yes, this is my hand-drawn diagram, Quinn, no laughing. Which way is this electron moving in the picture? The electron? Okay. Do we deal with an electron? No. Our right-hand rule only works for protons. So an electron moving to the right is the same as a proton moving which way? So all of you point your right thumbs to the left. What direction is the magnetic field in my hastily scrawn drawing? Okay, watch. Right when the electron gets here then, which way will it experience a force? Which way are all your palms pointing? Okay, it's going to get pushed down. Now it's traveling in that direction. So now an electron traveling down and right is the same as a proton traveling up and left. Point your thumbs this way. Magnetic field into the page. Now what direction will it experience a force? I think down and left a little bit. Yes? It'll kind of get pushed this way. Now for a split second, it's moving straight down. An electron moving straight down is the same as a proton moving which way? So point your right thumbs up, magnetic field into the page. Now it's going to feel a force this way. In fact, you know what? It's going to feel a force like that. Hey, this electron will be forced into I'm looking for a word that starts with letter C. Are you saying that electric force is what's pushing me in a circle? When we're talking about particles, yes. Now you know why particle accelerators, if you've seen pictures of them, what shape are they all built in? Circular. This is why. And this means that we can say, instead of like for orbits, gravity is what's pulling me in a circle, we can say electric force is what's pulling me in a circle. I like example 3. Example 3 is a nice question. Is there going to be a test? I don't know, but if there is, I like example 3. I like example 3. Example 3 is a nice question. An electron moving at 3.2 times 10 to the 7th meters per second enters a perpendicular magnetic field and it traces out a circular path. What's its radius? Okay. I got circular path. I got magnetic forces. You know what I can say? Magnetic force is what's pushing me in a circle. Read, what's our equation for magnetic force on a particle? Equals m. And then I need to decide which version of A am I going to use. Did this question give me or ask for a speed or a period? Oh, you know what? A speed, v squared over r. Yes? What are they asking us to find? Okay. Where is the R right now? On the? It's going to move to the top. How will I move the Q and the V and the B over? Divide. In fact, I'm going to get this. R equals mv squared all over QVB. In fact, is there a V squared on the top? Is there a V on the bottom? You know what? One of the V's will cancel out. I'll really get this. R equals mv over QB. Do I know the mass? It's an electron. Do I know the speed? Yep. Do I know Q? It's an electron. Do I know B? Tesla's 5.45 times 10 to the negative 4. I can do this. Mass of an electron, 9.11. What's the 10 to the negative 31? V, they told me, 3.2 times 10 to the 7th. Q, it's an electron, 1.6 times 10. I'm not going to put the negative in because a radius has to be positive. Yes, it's a measurement. So I'm assuming that now we're in Scalarville. B, a 5.45 times 10 to the negative 4. I was making up numbers. I hope I made up good numbers. I hope we don't end up with a radius that's like microscopic. I'm hoping we end up with a radius that's at least, what'd you get?
3.34 10 to the minus 47.
No. You missed a negative exponent somewhere. First of all, the digits are probably right. Sorry? 0.33. Anybody else? Come on. 0.33. How many centimeters? Yeah, about a ruler's length. So that's something that you would be able to see and notice. So this is some of what we do when we're doing particle accelerators. First of all, we can put a particle into any radius that we want. And primarily the way we do that is we change its speed. And how do we change its speed? Well, that goes back to our electrostatics unit. We can decide how many volts we're shooting it off with. Okay? How much energy per coulomb. So we can do that really accurately with circuitry. Or the other thing that we can do is if we're trying to figure out a mystery particle, if we know the radius, we can figure out maybe its mass if we know everything else, or its charge if we know the mass and everything else. So this is some of the particle physics that we do. I like example 6. I like example 4. Question 6, example 4. What do you think Jan 90 stands for? It's from the provincial exam from January 1990. I graduated in June 87. So if you ever see a question from June 87, you'll know, hey, that's the exam that Mr. Dewick wrote. Oh, sorry, my bad. June 1987. I can see a few of you 18. I know. How old is Mr. Dewick? Shut up. As shown in the above diagram, a proton entered a magnetic field at A. Is that correct? Let's see. Which way is the proton moving right when it hits the magnetic field? Up the page? Which way is the magnetic field? Into the page? Yeah, you know what? It would get deflected. See how my palm is moving around? It would get deflected in that area, and as its direction changed, the deflection would also change. It will get bent into a circle. The radius was 3.25 meters when the magnetic field strength was that. Ooh, Zaina, what's this question want me to find? You know, for all of these, is there a circle? Say yes. Magnetic force is what's pulling me or pushing me into a circle. We start with that. And we'll get whatever we need to by itself. Magnetic force, QVB. And mv squared over r. Zaina, one of the v's is going to cancel if I divide it over. I usually just do it on the first line. I cross out the squared and cross that out. What are we trying to get by itself? Oh! How will I move the m over? How will I move the r over? This isn't too bad. So, the speed is going to be QBR divided by M. Q, it's a proton. 1.6 times 10 to the negative 19. B, they must have told me, B is in Teslas. 2 times 10 to the negative 2. You know what? That's 0.02, which is less typing and less writing, so I'll unscientific notation it. R, 3.25. M, it's a proton. I know it's 1.67, but I can never remember the negative 27. There's a bit of an error check here. If you get something faster than the speed of light, you either won a Nobel Prize or violated or you're wrong. You're wrong. So you're going to get something less than 3 times 10 to the 8th. I hope. Zaina, what'd you get? When you're done, let me know. You'll find, though, usually you get stuff in the 10 to the 5th, 6th, or 7th range, because these things aren't just sitting around lollygagging. They're going to be moving pretty fast. What point what times 10 to the what? Is it 6 is it 6 point something?
I got 6.5.
I don't know. 6 point what? I've heard 6.5 and 6.2, so I need a group consensus. 6.2 what? 3 times 10 to the? Times 10 to the 4th? 6th, yes? Now, if you're lousy on writing stuff, meters per second, in scientific notation, you got several options. Most of your calculators can do it for you. I'll let you figure that out. Or learn to do it in your head, or just write out the whole number. But me, I'm naturally lazy. I learned how to do scientific notation in my head because I didn't feel like writing out all these big numbers. And I taught you how to do it in your head in Physics 11. Madison, is that okay so far? Okay. That's the force on a single charge. What about the force on a wire? Well, I'm going to argue that a wire is a bunch of single charges holding hands. So I think I can derive the force on a wire starting from the force on a single charge. So I said here, if we have a wire carrying current perpendicular to an external magnetic field, it will also experience a force because it's got moving charges. The direction of the force can be calculated using the right-hand motor rule. We practiced that, so you can get the direction. What about the magnitude? It depends on 3 things. The strength of the outside magnetic field. Stronger magnetic field, bigger force. Yeah, that makes sense. How big the current is. More current, more force, because more charges. And how much of the wire is inside the magnetic field? Because more wire, more charges, more forces. So it says, start with the magnetic force on a single charge. Well, that was QVB. Okay? And now let's introduce the notion of current. We defined current as the charges per second. Get the Q by itself, please. So this, by the way, some of you are looking, what? That was from last unit. That was actually the very first equation, even before Ohm's law, before V equals I times R. We defined current as, well, how many coulombs per second are coming by? How much charge is coming by per second? Finley, get the Q by itself. Sorry? Q is it. So I can replace this Q with what? Oh, not Q, Mr. Newick. Now do me a favor. Circle the T and the V. Now, really, instead of the T and the V, let's think of it as a V and a T. Do you know what V times T is equal to? It's distance. If we have no acceleration, we're going to assume these things accelerate in a split second, but after they accelerate, they're going at a constant speed. They might be changing direction, that's where the acceleration is, but they're in uniform circular motion at a constant speed. So we're going to ignore the plus a half AT squared. So I can write this as I distance times that. But this distance here is the length of wire inside the B field. What was B an abbreviation for when we're talking about fields? Magnetic field. We don't have M's taken. Okay? So as an equation, we write it this way. Look up. FB, magnetic force on a wire, it's Bill. But again, all three have to be at right angles to each other so that you can use your right hand rule. And otherwise, there is a component section and it's signed. I'm not going to ask you that, so I'm going to write it down. F is Bill. I think that's how I gave it to you on your formula sheet, right? Did I give it to you B-I-L? I usually write it as Bill, didn't I? Should be right next to F equals QVB, I hope. Yes? Okay. When do I use that? When I have a wire. What's the hint that you need to be using a wire? Current. The I. Okay? What's the hint that you have to be using an individual charge? Q for the QVB. So you got to keep your terminology straight. There's sort of variations of each other. Oh, sorry. Example 4. I like example 4. It says, find the magnetic force and the direction on the wire. Let's do the direction first. First of all, is the length of wire, the magnetic field, and the current, are they all in lovely right angles to each other? So I'm good with that. Okay? What direction is the current moving? Point your thumbs to the right. What direction is the magnetic field? So if I was doing my board, I would go like this, down the page. You know what I started to bend this way, and then I said, no. Just put my hand down this way. That works way better, because now my palm is pointing into my board. So, Mallory, you were doing none of this. This is the right-hand motor rule. Thumb extended at a right angle. Fingers locked straight. Not like this, locked straight. Locked straight. Thank you for the right-hand motor rule. So, ready, Mallory? It looks current is that way, yes? And then, which way is the magnetic field? It's downwards. So I could either bend and arc like that. Wait. Just do this. Put it down beside your hand, beside your body. That works easier. And your palm is pointing for all of you forwards, which relative to my board is into the page. So the first thing I would say is F equals. You could write into the page, but you know I'm going to abbreviate. Right? Okay? Now let's find the magnitude. F equals Bill. Why do I use a lowercase l handwritten? Why would I not want to write it this way? Yeah, don't do that. You can use a capital L. I'm not going to freak out. A capital L is technically taken by something else, so I use a lowercase handwritten cursive L. Just a habit. How big is the magnetic field? 6. How big is the current? 5. What's the length? Don't say 70. 0.7. Heck, I can do that in my head. Some of you might even be able to do that in your head as well. It's going to be 30 times 0.7. 21? 21 newtons into the page. Okay. We're getting very close to being able to design electric motors. We've reached the point where we can pretty much pinpoint how much force we want to exert on a single wire. Now we just got to figure out a way to make it spin. It just turns out not that tough. I don't think we'll get there today. We'll probably get there tomorrow. If the force on a 5 centimeter, nice try, Duick, 0.05 meters, piece of wire carrying 12 amps is that, what is the magnetic field strength of the perpendicular field? Ooh! What's this question asking me to find? What symbol is magnetic field strength? B. Okay. First thing I would do is write down F equals Bill. Okay. Mallory, get the B by itself. Yeah. Starting to see, I'm hoping you're realizing why I taught you so much formula manipulation last year, because to try and do these all individually, I would go crazy. Sorry, my bad. I would go crazier. I saw a few of you, Mr. Duick, crazy, Fair enough. All right. Well, Mal? No, I already picked on you for one of these. Maddie, what's the force? I'm going to write 0.001 because that's less typing. Divided by 12. And also divided by 0.05. How strong a magnetic field will I need to create if I want that big a force? 1.67 times 10 to the negative 3? 0.0016 repeating, I'll bet, yeah? Is that right? I see 2 people shaking their heads, so yeah? So those of you shaking your heads, Zaina, do you remember to put brackets around the bottom? Ready? Sorry? Is that right? Or 0.0016 repeating. Yes? Units. Get to use Teslas. Capital T. Always nice to learn a new unit or use a new unit for the first time. So, first of all, do you notice if I can control how big the magnetic field is, I can very much control how big a force. How big a force do you need? Let me know, and if I can create a magnetic field that big, we're good to go. So it leads to a question: how to create magnetic fields that big? Oh, actually, need application first. It's an older movie. Some of you may have seen it or read the book. There's a movie that came out in the mid-90s, 1990s, called The Hunt for Red October. You've seen it? Or read the book? Okay. The premise in there is a Russian submarine has invented something that they've called, in the book, it's nicknamed the caterpillar drive or magneto-hydrodynamic. It's a jet engine underwater with no moving parts. Here's the theory of how it would work. It's really quite clever. So magneto-hydrodynamics is the use of a magnetic field to propel ships or submarines. So what you do is you run a current, I, through seawater, because seawater is a good conductor, while the seawater is passing between large magnets. How will this propel the ship? So let me zoom in. First of all, what's the polarity of the magnet on the top? What's the polarity on the magnet on the bottom? Which way do magnetic field lines point? From what to what? Let's draw in 3 magnetic field lines. Okay, and I'll label that with the capital B for magnets. Alrighty. What direction is the current going? Those X's, what are they telling me? Okay, what's carrying the current? Water. Those are the moving charges. Water. So watch. Point your thumbs into the page, into my board. Magnetic field down the page. Good. Which direction will the water feel a force? Out the back like a jet engine, no moving parts. It's more complicated than that. But this was the theory that they were talking about in the movie. F would be that way. If you could, I haven't followed if they've actually managed to build this or not, but in submarines, it's all about who's the quietest. If you could design that, you would have an engine with essentially no moving parts, really quiet. Okay. Okay. So I said to you, all right, Mr. Duick, I get that if I can control the magnetic field, I can control how big a force, which means now I can start to control, once we get to electric motors, how fast the motor spins, which means, I can start to control how fast the motor is running. How do we control magnetic fields? The easiest is to use electromagnets, solenoids. So here's a model of a solenoid, a coil of wires, and it turns out the magnetic field strength depends on 3 things. Number 1, the number of turns or wraps of wire. If you have one solenoid with 10 turns of wire and an identical solenoid with 20 turns of wire, the solenoid with 20 turns of wire is going to have twice as strong a magnetic field. It's a nice 1-to-1 relationship, which is really great because it means I can pinpoint how strong a magnetic field I want just by the number of turns of wire. Oh, you need a stronger magnetic field? By how much? By 30%? Let's just add 30% more wraps. Good to go. Or it also depends on the current that you send through the wire. Stronger current, stronger magnetic field. Oh, if you want the magnetic field to be twice as strong, double the current. And then we found making them longer is not as good. The longer the solenoid is, the weaker it gets. The closer you can pack those turns of wire together, the more you can wrap them so they overlap, the stronger it's going to be. So here's what we found. As an equation, the magnetic field strength depended on N, the number of turns of wire, I, the current, divided by L, the length of the solenoid. The problem is number times amps divided by meters does not work out to Teslas. Much like we had to put a big G in front of our gravitation equation to get an answer in newtons, much like we had to put a letter lowercase k and have the 9 times 10 to the 9th constant to get an answer in newtons, to get an answer in Teslas, I get to give you perhaps my favorite named constant of all time. The actual equation is this. Magnetic field is equal to mu naught. You can say mu 0, but my high school physics teacher, one of my heroes, was British, and he always said mu naught, and so I'm going to call it mu naught as my homage to Mr. Cowell, times N times I over L. Now, this leads Clothy to an obvious question. What's mu naught? Not? On your formula sheet, go find it. It's with all the other constants somewhere.
4 pi.
Pi? What the heck does pi have to do with magnetic field strengths? And this is, well, there's some circular, but also read, this is just, the universe seems to be nuts about certain constants. And one of them is pi shows up in bizarre places. Places where there's nothing to do with a circle, and yet, ha! There's pi. Yeah, what is it? 4 pi times 10 to, is it negative 7?
Yeah.
And then whatever the units are. I'll find it. It's going to be right where the big G is and right where the little K is. It's in that same chart. Okay? And it has, to me, one of the coolest sounding names. What's it called? The permeability of free space. Reed, what did you learn in school today? Mummy, I learned about the permeability of free space. Oh, Reed, you are ever so clever. Thank you, Mummy. Right? What a great name. And yeah, nerd note, pi rears its head again. It just shows up in cool places. There is a second version of this equation that's used in industry. Sometimes you don't know how many coils of wire and the overall length. Sometimes all you know is the number of turns per meter. Okay? Sometimes the equation is written as this: mu naught lowercase n times I, where lowercase n is turns per meter. You'll know that if they don't give you the length of the solenoid, but they tell you the number of turns per meter. Use this one. If they tell you the total number of turns, and they tell you the total length of the solenoid, use the first one. Let's jump on in and try some of this. Okay? By the way, what this does then is, Zaina, this gives us a way to really very accurately customize our magnetic field, because I can change 3 variables. I can change the current. That we've learned enough circuitry to realize you can do that out on the field by just changing the amount of amps flowing through your circuit by adding or changing resistors. We have very good control over that. In the factory, while you're building the solenoid, you can change the number of coils of wire or how long it is. So I can very accurately give you whatever magnetic field strength you need. I can do it. A solenoid is carrying 4.2 amps. If the solenoid is 1.2 centimeters, nice try, Duick. 0.012 meters long, and is made up of 750 turns of wire, what's the magnetic field at its center? By the way, the magnetic field strength we're talking about is dead center of the solenoid. Not to the left, not to the right, not above, not that, because the further you get away, the weaker it gets, but dead center, this is the magnetic field strength. Okay, Claudia, what does it want me to find? Okay, and we're talking about a solenoid, so we're going to use the magnetic field of a solenoid equation, which is, what is it? Mu naught n times I over L. I think that's right, yes? Where mu naught was 4 pi times 10 to the negative 7. N was the number of turns of wire. By the way, on the previous page, I should have listed this. So let's say N equals number of turns. And we all know what I is. What's I at our abbrev for? Current. So if you want to write that, you can, but if you know it, you don't need to. And L was the length of the solenoid. So the more you can pack the wires together, the better. Anyways, what's N here on this example that we're doing? 750. Current, 4.2 amps. 0.012. Every one of you needs to try typing this in, because about half of you are going to get an error on your calculator. I won't tell you where yet, but all of you try typing in 4 pi times 10 to the negative 7 times 750 times 4.2 divided by 0.012. And if you get an error, let me know. Okay? So your software won't let you do scientific notation with pi. And I don't know why, but it's a software glitch. So for you folks, instead of typing 4 pi, look up. You'll type pi times 4 scientific notation. It'll do scientific notation with a number. I would argue pi is a number, but what brand are you? Sharp, Casio, or TI? Yeah, I think it's the Sharps that this is an issue for. It might be an issue on the Casios too. Times 750 times 4.2 times 0.012. I know on my TI graphing calculator, I can do pi scientific notation button and not get an error, but I know on a lot of those calculators you do. So the cheap, easy workaround is flip the 4 and the pi around. Yes? You're going to get that, I think. Let me pause for a second and come. Don't clear your calculator. And of course, I was distracted and made a mistake. People on YouTube were screaming at me. I went times by 0.12. Should have gone divided by 0.012. Do you get 0.33 units? Teslas. Okay. Two more we're done. Find the field and the direction at the center of the coil. The coil is carried. So this is my limited graphics. We're looking down the solenoid like a telescope. We're looking through it. That's why you just see a circle. If you are a good artist, you can say we're looking like through it like that along the end. I suck at drawing these, and so there's my limit for graphics. But imagine we're looking through the tube of the solenoid. Okay? First of all, well, let's find the field. B is going to be. Now, before we start writing anything more, did they give you the current? Did they give you the total number of coils? No. Did they give you the length? No. What did they give you instead? Coils per meter. So we're going to use, and I think I gave you this formula, this second one on your sheet as well. I think I gave you both, yes? It's going to be still mu naught, but instead of capital N times big I over lowercase l, it's just, someone's already done N divided by L and simplified it to lowercase n. Turns per meter. Okay. Mu naught, 4 pi times 10 to the negative 7. Figure out how you have to type that into your calculator. Times 2550 times 10. Some of you were saying over here that if you just added an extra times, I would still type pi times 4 scientific notation button, because putting a times in front of scientific notation can sometimes lead to really obscure, weird glitches, especially if you're dividing. Because the software doesn't know what's part of the scientific notation number and what isn't. Or just be really careful with brackets. I have no idea what the answer is. 4 pi. No. Oh yeah, mine works. So I don't get an error. And if you have the TI graphing calculators, I think the TI's, the software handles it okay. It's the other ones that don't. Is it 0.032? Units, Teslas? Ooh, it wanted the direction of the magnetic field. So we're going to use our right-hand solenoid rule. What was that one? I heard somebody say earlier in class, the solenoid one is the one I understand. Pretend you're holding the solenoid. Now, the only way that I can hold this solenoid would be if I had my hand oriented like this or like this, if I'm using the board as my reference. I curl my fingers in the direction of the current. Gotta be this way. My thumb points north. Is the magnetic field coming out of the page towards us or into the page away from us? Out of the page towards us. How can I show out of the page? What's my abbrev? Zana. There's the direction of the magnetic field. You're going to get a bunch of homework tonight, but there's not any homework attached to tomorrow's lesson, so you can work on it tomorrow, and you'll get a take-home quiz tomorrow as well. One more. All right. Suppose you're a manufacturing company. You manufacture solenoids. And the company has said they have a 30-centimeter opening, that's as big as it can be, and they need a magnetic field of 6.28 times 10 to the 3 Teslas. Yeah, and all we can put through here is 5 amps. We've designed our circuit. We can spare 5 amps for the magnetic field. How many wraps of wire do you need to put around your solenoid? Well, this is the magnetic field for a solenoid equation. So it's going to be mu naught N times I over L. I knew to use this one because they gave me the length in the question. Although I probably would have said, nice try, Duick, 0.3 meters. Okay. Wolf, what are they trying to get me to find? Which variable is that? Use the process of elimination. Is it B? No. Is it mu naught? No, that's a constant. Is it I? That's current. Is it L? That's length. What do they ask? What? Yes. What does N stand for? Number of turns of wire. Okay? Get the N by itself. How will I move the L over? How will I move the mu naught and the I over? So you're telling me, if I'm in the factory, I would go N equals B times L divided by mu naught I? Yes, I would. It's going to be B, 6.28 times 10 to the negative 3, L, 0.3, divided by 4 pi times 10 to the negative 7. How many amps? 5. I tried to make this one work out almost evenly. You might have to, I'm hoping you get an answer like 0.999 or to a whole number, because technically it should be a whole number of turns. I hope. Finley, what'd you get? 4,998? No. 299? Anybody else? Is it 299? Is that right? I'm seeing a lot of shake. Yes? 299.4? 0.84. How many turns? 300. Okay? That's what I started with when I made up this question. And the units for turns, believe it or not, is turns of wire. And by turns of wire, once around is 1 turn of wire. Okay? Good stretch? Okay. Okay. Now, one of the nice things, this was always a nice unit to wind up with because you'll notice the math part of things has been pretty, oh geez, I can rewrite this stuff in my sleep. And it's kind of interestingly neat. The tricky part is keeping straight all of the variables and terminology. Yeah, I got that. So, practice. What are we going to work on? Number 1. In number 2, it's floating due to gravity down and magnetic forces up. So in number 2, you can write gravity equals magnetic force. You can write mg equals Bill. And then they're asking you to find B. We're also getting closer to hoverboards and things like that. You can make stuff levitate magnetically. Three is good. Skip 4. 5 is good. 6 is good. 7 is good. 8 works. Skip 9, or as I like to say, 9. 9. Oh, this is straight plug and chug. 10 works. 11 works. 12 is good. 13 is good. 14 is good. These are all conceptual. 15 is good. And 16. You'll get time to work on these tomorrow in class. Yeah, 17. So this is not due tomorrow. Believe it or not, ready? We're basically done this short unit. I'm going to show you some cool applications tomorrow, but no new equations. You can also start to whittle away at the ultimate review if you want to. Wow, you were just jonesing for that phone, weren't you? Boy.